Hi, everyone. So today we are going to be learning about Hess's law. So, Hess's law is just a way to calculate the enthalpy of a reaction when we don't know the standard enthalpy of formation of the reactants or the products. So, what we're going to do here is we're going to use the heat of reaction from other reactions to calculate the equation with an unknown heat of reaction. Now, the reason this works is that because we're going from a particular set of reactants to a particular set of products, the change in enthalpy will be the same whether the reaction takes place in one step or a series of steps. So it could be multiple steps. You could be going through all of these different reactions to get to your products. And then what we'll end up doing is we're kind of adding all of the enthalpies together at the end, and you'll see that things cancel out as well. So I have an example, like a mathematical example over here on the right-hand side of the screen. So this is kind of similar to like when you have two equations and two unknowns and you're trying to figure out what those unknowns are. Because I can cancel that 2x out, I can then find what y is. And so you'll see that this is kind of the same idea. It's kind of like a puzzle. They're kind of fun to do, I think. So hopefully you feel the same way. Now, in these problems, you're going to be given an overall reaction with an unknown delta H, and then you're going to be given two or more reactions with a known delta H that you need to manipulate so that you can get that overall unknown reaction. So, for example, here, this is my overall reaction where I don't know what the delta H is, and then I'm given these three chemical reactions with known delta H's, and then from these three, I need to manipulate them so that I end up matching that first reaction. So I'm going to show you how we do this right now. So again, here's our reactions. Now, the first step here is that we want to find substances in each known step that are in the overall reaction, but not in other known steps. So for example, here, this carbon that I have on the reactant side in the overall reaction, I can see that it is in my first reaction that I know the delta H for, but you can see that it's in the products, which is not where I want it to be. And it also only has a coefficient of 1, whereas in the overall reaction that I want to find the delta H, the coefficient is 2. So there's going to be two things that I need to do in order to manipulate that equation, and I'll get to that in a second. Another one that is in the overall reaction and in one of the steps, but not all of them, is this methane, CH4, right here. I can see that in my overall reaction, it's in the products. And then in that third chemical reaction, it is in the reactants. So I'm going to need to manipulate that one and so that those match in location. And then last but not least, I have this carbon dioxide here in the products in my overall reaction. And then I can see that it's also in the products in the second chemical reaction. So the next step here is that we want to then check to make sure that the substances in the known step match both the coefficients and the side of the overall reaction. So you can tell I was already kind of mentioning this with the red circle around the carbon. See how that carbon in that first chemical reaction is on the product side? So I'm talking about this right here, right? It's in the product side, so it doesn't match the side where I want it, and the coefficients don't match. So I'm going to have to manipulate this. Now, in order to manipulate the side of the reaction, we're going to flip it. And when we flip this thing, we have to also reverse the sign of delta H. So let me show you what I mean by that. So this first chemical reaction, the first thing I'm going to do is I'm going to flip the whole thing. And when I do that, I also need to reverse the sign. So instead of a negative 131.3 kilojoules, it's going to be a positive 131.3 kilojoules. So you can see here, now I have my carbon on the same side where it's supposed to be in this overall chemical reaction. However, I'm not done yet, right? You can see in the overall reaction, I have a 2 coefficient in front of the carbon, but I don't have a 2 here. So I need to also multiply everything through by 2. So when I multiply and divide by a coefficient, I have to do the same to the delta H. So I have multiplied through everything by 2 as well as the delta H. So now my overall delta H for this first reaction is a positive 262.6 kilojoules. And then now I can see that my carbon, that location matches with where I want it to be. Now, for the second one right here, I can see that this carbon dioxide is exactly where I want it to be, right? I want it to be in the products. I also want it to have a coefficient of 1, so I'm good. It's exactly where I want it to be. That delta H is going to stay the same at negative 41.2 kilojoules. And then last but not least, I can see with this equation here that I have my methane in the reactants, but I want it to be a product. So I'm going to have to flip this whole equation. And then when I flip it, remember we have to change the sign of the delta H. So that's going to be a negative 87.9 kilojoules. I don't have to do anything else with this because look, there's no coefficient in front of this methane here. There's none here. So they're both a 1 coefficient. And so that's the only thing I have to do. I just have to flip it there. So here's all of our chemical reactions now flipped. So I have a positive 262.6 kilojoules for that first one, still staying at that negative 41.2 kilojoules for the second. And then I flipped that last one too. So that's going to be a negative 87.9 kilojoules. And then now what I want to do is I want to add the steps together to get the delta H. Now, when I do this, I also want to cancel things out just so that I'm making sure that it actually matches that overall reaction. So when I do this, I like to actually draw a line like this because I'm going to be adding downward. Now, I like to think of that arrow as like a barrier. So when I cancel things out, and I'll show you what I mean right now. So first and foremost, I can see that I have this carbon monoxide in that first one where that little line is. I have 2 carbon monoxides on the product side. Now that carbon monoxide, both of those carbon monoxides are going to cancel out with this carbon monoxide in that second one because that one's on the reactant side, and also this other carbon monoxide on the reactant side. So I have 2 carbon monoxides on the reactant side, 2 carbon monoxides on the product side. Those all cancel out, okay? Next step right here is I want to cancel out this hydrogen. Now I have 2 hydrogens on the product side in that first equation, and I can see I also have 1 hydrogen on the product side in that second equation, and these are going to cancel out with those 3 hydrogens in the third equation on the reactant side. Okay, so now all my hydrogens have canceled out. Last but not least, I can see that, look, I have look at all my waters. I have 2 in the first equation in the reactant side, 1 in the second equation in the reactant side, and then I have 1 in the products in that third equation. So one of those waters on the reactant side are going to cancel out with one of the waters on the product side. Now all I have to do is I just have to add downward. So I have the 2 waters plus 2 carbons in the reactant side of that first equation. And then I have CO2 from my second equation on the product side, and I have methane, CH4, from that third equation on the product side. And then all I do here is I add those delta H's all up together, 262.6 minus 41.2 minus 87.9, and I end up getting a 133.5 kilojoules for this overall reaction. So those are the basic steps for Hess's law. We're going to do 2 more examples, okay? So hopefully it gets a little bit easier and it makes a little bit more sense. So example number 2 here. We want to calculate the delta H for the combustion of methane. So going through our steps, first we want to locate where we have certain things in this overall chemical reaction that we want to know the delta H for, and that are in one step but not all of them. So the first one right here, look, we have methane. Methane is in the reactants in the overall chemical reaction, and I can see that it's in the products right here. So my first thing is I'm going to want to probably flip this equation, right? Because I want it to be in the reactants. So I flip this equation. I then have to change the sign of my delta H because I flipped it. So instead of a negative 74.8, it's going to be a positive 74.8. Now the next thing here that I see is, look, I see 2 oxygens, and I have 2 oxygens on the reactant side. Interesting. I also see that I have that carbon dioxide on the product side in my overall reaction. And look, it's the only carbon dioxide that I have is in the second equation, and it's also on the product side. So that carbon dioxide is happy. That second reaction is happy. I'm not going to do anything to it. I'm just going to rewrite it right over by my other one. Okay, so that negative 393.5 is staying exactly how it is. And then last but not least, I have my 2 waters, my 2 H2O. I can see that I also have 2 H2O in the products on my third equation. So I'm also going to write that one exactly how it is. So now all I have to do, add them all up together, cancel some stuff out. So I can see that I have a carbon on the product side in that first equation. I also have a carbon on the reactant side in that second equation. So those two things cancel out. Something else that cancels out, look, I have two hydrogens in the product side in that first equation, and I have two hydrogens in the reactant side in the third equation. So those two things cancel out. And then now I can just add everything all up together. I get that methane plus two oxygens reacts to form carbon dioxide plus two waters. I add all those delta H's up together and I get a negative 890.36 kilojoules. So you can see sometimes you don't have to manipulate the chemical reactions at all, right? The only thing I had to do here was I just had to flip that first equation, but the other two I just kept exactly the same. All right, last but not least, this is the first one from the Hess's Law practice that I have linked on Canvas. So I can see I have two chemical reactions here. Now, for this one, I can see here that in the products, I see something that matches. That's not in the other one in my first equation. So that's C2H6, dicarbon, what is that? Hexahydride. I always get 6 and 5 mixed up for some reason. So C2H6 I have in my products. It's in my products in that first reaction. However, I can see that it's also that the coefficients don't match, right? I have 3 in my overall equation, but I have 1 in my chemical reaction where I know the delta H. So the thing that I'm going to have to do here is I'm going to have to multiply this thing through by 3. And so that means I multiply everything through by 3. I'm going to multiply that coefficient of 2 by 3. That's in front of the carbon. I'm going to multiply 3 times 3 in front of the hydrogen. I'm then going to put a coefficient of 3 in front of my product there. And then I'm also going to multiply that delta H by 3 as well. So we get 6 carbons plus 9 hydrogen gases react to form 3 C2H6s, and then I multiplied that delta H by 3. So I get negative 60.6 kilocalories per mole. And then I can see that in my overall reaction, I have 2 C3H8s, right? And that's in my products here in that second chemical equation. So I can see that not only do I need to multiply through by a number, but I also need to flip this chemical reaction because it's in my reactants in the overall chemical reaction, but it's in the products in the given chemical reaction. So what I'm going to do here is I'm going to flip it and I'm going to multiply everything through by 2 because there's a coefficient of 2 in my overall reaction, but I don't have a coefficient. I have a coefficient of 1 in front of this one right here. So I also have to multiply everything through by 2. So we flip it, we multiply everything through by 2. So I have 2 C3H8s, and then I have 6 carbons and 8 H2s, hydrogens. And then with this delta H, I have flipped the sign, so it's now a positive, and then I've multiplied it by 2, so I have a positive 49.6 kilocalories per mole. Now I'm going to cancel some stuff out, add everything up together. So it looks like I have 6 carbons on the reactant side from the first one. I have 6 carbons on the product side in the second chemical reaction. So those two things cancel out. And then look, this is interesting. I have 8 hydrogens in the product side on the second one, and I have 9 hydrogens on the reactant side of the first chemical equation. So what happens here is that what we're doing here is we're actually subtracting. So I'm going to subtract 8 hydrogens from both sides. And so what happens is 9 minus 8 is 1. So I'm still left with 1 hydrogen on my reactant side. So here I get 2 C3H8s plus hydrogen, just 1, because remember I still had 1 left over there. And that reacts to form 3 C2H6s, and then adding up negative 60.6 plus 49.6, I end up getting a negative 11 kilocalories per mole for this overall chemical reaction. So there's your 3 examples for Hess's law. I hope that this made a little bit of sense. There's some practice on Canvas if you want to practice yourself. There's also that checkpoint that I do want you to turn in. If you're having any trouble, remember you have a work day tomorrow. You can always email me if you have trouble or just come in and ask some questions anytime. All right. So good luck, and I will see you in class.